3 use cases, but we have the associated applications. For example, this will be used in smart cities, smart buildings, etc. And the URLs will be used in the e-health for connecting the ambulance or remote consulting, etc. And similarly, the gaming with augmented reality needs a lot of bandwidth, high throughput. And if you want to create a 3D rendering in augmented reality or virtual reality, then we need to have higher data rate. So all these applications can ask a question whether the 4G or LTE cannot support it. The 4G LTE data rates are limited, maybe in the rate of around a few 10 Mbps, right? Few tens of Mbps is what we are going to get. And moreover, the latency here will be in the order of 10 millisecond or tens of millisecond. But if you are going to do gaming and other things, robotic control, you need around sub-millisecond. Less than 1 millisecond kind of latency you need. So all these different applications drives us towards 5G. Now, what are the things available for us as a network parameter? What are the things the operator can control? Operator can be Airtel or Reliance or Vodafone, anybody, right? Let me see, erase the whole thing. How? Okay, so now if you look at what are the parameters network can offer us, the operator can give us, right? One, bandwidth, higher bandwidth. So for FR1, they can go up to 100 megahertz. And for FR2, they can go up to 800 megahertz. 400 to 800. 400 is what today being deployed. 800 is in the plan. Okay, so that is one. Then what else they can provide us? Higher transmit power, more antennas, what else can be given? Let it be a communication, two-way communication. One-way communication means I will not get any feedback whether you are listening or sleeping. Somebody can speak.
Students, please participate. Students, please participate along with the sir. So, sir, they have given information in chat, sir, low latency.
Okay, low latency.
It is there in the chat, yes, sir, yes, sir. Surya Kumar has answered, it is low latency.
Okay, good. Right? So these are the things that they can give. So from there.
Sir, one more thing, spectrum efficiency, Sivashankar.
Good job. That's a good one. Efficiency.
Students, you can students, you can unmute your mic and then speak.
Yeah.
Because sir may want to hear your voice.
Yeah, I'm not looking at the chat window now.
Yes, sir. Yes, sir.
So these are the things that network operator can provide us. Now, from this, we need to, for each application, You need to map, okay, what is the bandwidth I need? What is the latency I need? What is the spectral efficiency I need? What is the power I need, right? And that particular mapping is what done by the standard 3GPP standard. If you take the latest version is release 17. However, the first release of 5G started from release 15 onwards. Release 17 is current. Release 15 is the first 5G standard, and there are going to be 2 more revisions. So each revision, they keep adding more and more features. And that feature is the one which basically is going to make us or provide us this or various applications that we have listed here. Oh, not selecting. Okay, clear. Now let's move on. So now we are all know that this one is a wireless channel. We all studied about wireless channel. What are all the issues in wireless channel or advantage in the wireless channel? Somebody can speak. Come on. You need to.
Sir, they say fading.
Okay.
It is there in the chat. They say fading.
Yeah, don't use chat box. Fading. What else? Fading comes from a phenomena. What is it called?
Sir, one more. Say people say it is a high data rate. Wireless supports high data rate.
Why high data rate?
Shiv Shankar, why high data rate you say?
Don't worry, this is not a test. This is only just we are exchanging knowledge. Even if it is wrong, it's okay. I just want to understand the thought process.
Shiv Shankar?
Okay, fading comes from something called multipath channel. Wireless channel will have multipath reflections. We'll see that more details. And high data rate will come only if can provide higher bandwidth, which is possible in wireless channel. Otherwise, it is no. Otherwise, it will be lower than wireline channel for the same bandwidth. And another thing it can provide is something called diversity. What is diversity? Because of the multipath, we are receiving signal through multiple copies. Same information is transmitted in multiple copies. That let's see whether it is advantage or disadvantage. Okay, you can tell me whether it is advantage or disadvantage.
Students, all of you, please participate.
Okay, this eraser is giving me trouble. Let me go for wire.
கொஞ்சம் எல்லாரும் participate பண்ணுங்க.
It's a Bluetooth. தமிழ்ல பேசணும் பேசணும் ப்ராப்ளம் இல்லை. Okay, some problem. So here. Never mind. Okay, so let's move on. So when you have one transmit antenna and one receive antenna, and there is a channel limiting, This we call it a CISO channel. Single input, single output channel. Right? Now, what are the issues with a channel? We'll have path loss, which is attenuation of signal going through the wireless medium. Typically, wireless medium has more attenuation than wireline channel. And the channel is dynamic. That is another important factor. That means even though the base station and the mobile are not moving, if the channel keeps changing because of the environment. Suppose the bus comes here, right? You get additional path. Or you get auto coming in between, or something else coming in between, a tractor coming in between. You are going to get an attenuation because you are kind of hiding the direct path, right? So the channel is dynamic. It is changing every milliseconds. And now when you have multiple users, multiple base stations, each of them will interfere with each other. This guy will go here, there, here, everywhere, right? And similarly, this guy goes here, there, here. So there is an interference in the channel because it is wireless in nature and nobody can control that. It is nature. So what are the things that we can control? These are all things that we cannot control. I mean, we can control to a certain extent, not everything. Okay. So now what are the things that we have control? We have control on transmit SNR, which is related to the power, right? And that is one thing we can do. What else we can do? Somebody can answer that. See, if you are not responding quickly, then we are going to take more time. So we will lose time unnecessarily, and you will not be able to. I mean, at least I will not be able to cover all the slides.
Students, please participate.
Okay, just to make the thing easy on you, we have structured this talk like this. First, we'll have about 1 hour talk. Then we have a 1 hour MATLAB session. And we'll have the rest of the timing for the remaining slides. This is how it is planned, so that you'll have some time in between where you can try hands-on. So if you are going to not respond, then I have to cut time on the MATLAB. That's the only way I can cover the slides. You guys decide what you want to do.
Students, please participate so that you can learn more from sir. All of you, please participate. Sir, Aishwarya has given diversity can be employed, sir.
Okay, good answer.
Yes, sir.
What is diversity? Aishwarya, you can respond.
Sir, it says overcome deep fade, sir. Sir, she given a response that it overcomes deep fade.
Okay, that's a valid answer, but not the correct. I mean, not the final answer. It kind of means it's a means. I mean, it is more like a.
Sir, one more answer from Surya Kumar. More transmit and receive antennas gives diversity.
Good. So more transmit antennas.
Aishwarya says it is introducing multiple links.
gives you multiple paths. Even if channel is not giving multiple paths, you should be able to have multiple connections. You have these connections and you have these connections, right? That way you have redundant information. That's called spatial diversity. We can also give diversity in frequency, time slot, and coding. There are other means of doing diversity. And 5G employs all of these techniques. Everything is used to get all the advantage that one can benefit from the technology wise. Okay, so now let's move forward. So what are the advantages in the CISO channel, wireless channel? We can have non-line of sight communication, which is not possible if it's a wireline. Wireline or fiber optics, we need to have line of sight or a physical connection. Multiple paths provide multiple copies, redundancy. This is diversity. I can transmit same information on to two different frequencies or two different time slots or two different codes or two different antennas. We can have same information shared between the transmitter and receiver by exploiting all these possible diversities. And 5G uses all of them. I hope at the end of the lecture today, you get the feel for it. Okay. So we have the diversity. And now you can also send multiple information simultaneously. How? Which is called multiplexing. Basically, I have two antennas. Instead of sending same information in both, I can send X1 here, X2 here. I'm going to receive these two copies in the two receivers, right? These are the channel coefficients. I'm going to receive Y1 as H11 X1 plus H21 X2 and Y2 as H12 X1 plus H22 X2. So I have two different signals carrying the same information but multiple information. This is called multiplexing. I can do that in wireless channel. In wireline channel, it is not possible. Only if I can separate them in frequency or time. On the same time and frequency and code, I cannot do this in wireline. In wireless, I can do that. Okay, so appreciate that difference. So even though wireless channel throws a lot of challenges at us, we are getting benefited from these other intangible benefits. Not straightforward, but there are like something which is available for you to make use of it. And what else you can do? It can be deployed anywhere you want, even inside building, in a mountain, between Earth and Moon, everywhere, right? So in fact, now people are talking about extraterrestrial communication also. How Mars lander and other things which are communicating with Earth is using the wireless channel. Okay. So now let's little more details on the CISO channel. I mentioned that you have one transmitter and one receiver, and there are multiple paths through which it can be received. So the received signal y of t is going to be sum of ai x of t minus tau y. Multiple time delayed and amplitude weighted, phase weighted signal is what will be received here. Now, depending on these delays or the phase values, right? It can be a power r e power j5 complex number. These signals can add in phase or add in opposite phase. So depending on the phase addition, the signal can be strong or weak. That is what we call it as fading. The signal strength varies over time, even if I transmit same power. So that's problem number 1. How can we solve it? Simply boost the transmit power such that even the lowest signal here level is good enough for your reception. That is one way to solve. Is there any other way to solve? Not that easy. So another way to solve is coding, but let's not go there. So now let's look at how the bit error rate curve looks in a SISO channel. If I am a wireline channel or line of sight channel, I'm going to get a bit error rate with a SNR like this. This is for a BPSK signal. So you are going to get 10 power minus 6 around 10 dB SNR. Okay. But same thing, if it is a wireless channel, even for 10 power minus 2, I need about 25 dB. Why is that? This is because of the fading phenomena. And how we can get it? This is the bit error rate for a AWGN channel with SNR P by N naught. You would have seen on the textbook Q of square root of SNR. Okay. Now, what has happened is because of the fading, this signal level is changing according to distribution of this. Let's say this is Rayleigh distributed. One type of channel, right? For that, if the combined bit error rate, what we are going to see is this integral value. We are going to integrate across all possible values of P with its probability. And that's how you get the average bit error rate. That average bit error rate is what is plotted as a green curve here. This is the same guy for a wireless channel. This is for wireline channel. This is for wireless channel. So, as you can see, we need about 20 plus extra dB. Even to get 1% bit error rate, we need to get about 20 dB extra. Here it is 5 dB, there it is 25 dB. Okay, that is an issue. So now, how do we solve? Even though we have many advantages in the wireless channel, we are going to face this issue of higher transmit power. That's where the diversity comes into picture, where we use multiple antennas. Okay, I hope you understand. Let's say I have 3 antennas. Okay. 3 transmit antennas and 1 receive antenna. T1, T2, T3 to R1. So I have 3 independent paths, H1, H2, H3. So I'm plotting the strength for each of those channels. Let's say blue is one, red is another. Let's say one more color hidden in between. Sorry, magenta is there, another one. Right? Each one of them fail independently because they are independent paths. And now what I can do in the receiver, I can select highest SNR in each one of them or among 3 and pick that signal. Right? That is possible, right? Very much possible. And that gives me the advantage that I am going to pick a strongest signal. That means my received signal strength is this. It is always above, guaranteed to be above some value. If I draw a threshold like this, I'm guaranteed to be above that if I have 3 channels, right? And for that, you can see the bit error rate curve comes down drastically. In other words, I need slightly more SNR, not 20 dB, if I use multiple antennas for either transmission or reception. Both ways it works out, right? If I have, let's say, 2 transmit, T1, T2, and 3 or 4 receive, R1, R2, R3, R4, right? Now, what is the order of diversity? In this case, with the 3 antennas, the order of diversity is 3 independent paths. Now, what is the diversity order here? Somebody can respond. Don't sleep.
Hello, students.
2. He has given the answer.
Sir, answer is 2, sir. It's 2, they say, sir.
2, huh? Why 2? We have 2 transmit antennas, but 4 receive antennas, right? So let us count number of independent paths. From antenna 1, I have 1, 2, 3, 4. From antenna 2, I have 1, 2, 3, 4.
Sir, there are 2 more answers, sir. Surya Kumar has answered 2 cross 4. Lavanya has answered 8. Aishwarya has answered 2 power 4. There are many answers.
Actually, 8 is the correct answer. We have 8 independent paths as I drawn. So we have 8 order of diversity. Okay. If I plot the bit error rate for that, it will be very close to this. 8th order diversity. And that is what we exploit. Okay. And this particular diversity comes from antenna. So we call it as antenna diversity or spatial diversity because the antennas are spaced apart in geometry, physical dimension. Okay. Okay, good. Now you guys are getting the hang of it. Now let's move forward. What are the things that we have in our control? As we saw, we can control number of transmit antennas, receive antennas, right? And we can send identical information, all of them. So I'm going to get a diversity order of NP into NR. This many order of diversity I'm going to get if I send identical information in all. What if I send different information in different antennas? Will I get the same diversity order? Somebody respond? And the next question is, can we split the number of wireless channels into M groups and send different information on each of the groups? How do we decode? How will we manage the interference? how to do a smart coding instead of just repeating them, and how do we transmit higher power in channels where the link is weak. So for example, we have the, let's say 2x1 or 2x3. If this link is very weak, I can jack up the power here. If this link is strong, I can reduce the power. So that way I conserve power. Right? Similarly, I can do what I can do here. So that is all the relevant questions that one can answer. Okay, so I hope it gets rest by the time you move. So now we saw that multiple antennas is giving us advantage, right? And that is called multiple input, multiple output channel, otherwise called MIMO wireless channel. This is the channel for which you are feeding multiple inputs, 1, 2, 3, 4, which is NT antennas, NT inputs. And then we have NR receivers, and we have all these outputs coming from the channel. So we have multiple input, multiple output in the channel. So now it can be mathematically described as a matrix. Sorry. So we have Y1, Y2. It is going to be received from, say, 2 receive antennas. I'm going to say 3 transmit antennas, X1, X2, X3. Then I have this channel coefficients weights. Understood? So basically, every symbol is multiplied, or every transmission in a particular time slot 1 is multiplied by this matrix, and that is what is received in the receiver. Sorry, there are only 2 receivers, so there are only 2 by 3 paths. Okay. Okay, now let us see whether all these paths are purely line of sight path. No, they need not be. Some of them can be line of sight, some of them can be non-line of sight, or multipath. So for example, if we go back to the previous example here, so there is one line of sight path, and there are multiple non-line of sight paths. So there's one comes from here, one comes from here, and so on, right? So it can be a combination. So that is also can be incorporated in the channel model. Now let's look at how does the channel model differ in these 2 frequencies, below 6 gigahertz and the millimeter wave. In the 6 gigahertz, we have line of sight, reflection, diffraction, and scattering. In the millimeter wave, if you look at it, it's primarily line of sight only. Why? Because of the high frequency, whenever you have multiple reflections, they get attenuated faster. As a path loss, when the higher the frequency, you have more attenuation in the channel. Okay, problem number 1. Let me come back to this, why I call it problem. Then line of sight path loss is small, as I mentioned. Here, even the line of sight path has 20 dB larger attenuation compared to this. Why? The frequency has gone up by 10 times. So the loss goes up by 100 times, 10 square. So that is why it is 20 dB loss, extra loss compared to this. We are trying to compare, right? So this has less loss, and this has only line of sight, And shadowing is less in this one because frequency is less. Here is much larger because again, higher the frequency, more loss. And here the ray can travel around the edges. For example, I'm in a corner, let's say this is the T junction, and I have a transmitter here and there is a receiver here. Although there is no direct path, I can get reflected path, or even the ray bends around the corners and reaches here. It can come here, it can come here, some multiple ways it can come. That will not happen in the millimeter wave because it's only line of sight works because of the higher attenuation. Okay. And weather is not so much influence, but here a lot of attenuation coming from rain, fog, dust. Because the wavelength of the signal is coming in comparison to the size of the interfering or scattering objects. Okay. But one good thing is there's more bandwidth available here. Here is only maximum 20 available. So we have some advantage and we have some disadvantage which we need to cater to, we need to solve. So that is a challenge for engineers. As an engineer, if everything works well, you don't have a job. Why that extra loss in the higher frequency? If you look at the path loss computation, it is it's a function of lambda square and distance square. So as lambda becomes smaller and smaller, which is for higher frequency, you get higher loss. Or if the distance is higher and higher, you get higher loss. This is only for line of sight. Non-line of sight is a different ball game. Okay, so even line of sight you have a problem when you go to millimeter wave frequency. And that's why this lambda square is 1 by f square, c square by f square. And when the frequency becomes 10 times more, f square becomes 100 times less or more. 1 by f square becomes 100 times less. And because of that, you need additional 20 dB in the path loss. What does that mean? That means your cell size will shrink. If I have 10 kilometers radius in the FR1, FR2 I am going to have 1 kilometer radius, 10 times reduction in the coverage, cell phone coverage, which we don't want to do. So that's where these various releases of the standard 3GPP standard comes in handy with the different technological advantages. Okay. So what are the technology advances? In release 10, which is LTE advanced, we had up to 8 multiplexing, antenna multiplexing, or diversity, one of them. You can do both, or one of them, not both. You can get a combination, but you cannot get maximum in both. Okay. So that's old technology, age-old technology now. We are come past that. If you look at release 13, which is the latest version of LTE, actually there is a release 15 also for that. Let's not worry about too much. There is a release 15 LTE also, apart from 5G, with improvements. If you see what they have done is, here it's fixed codebook. Here it is dynamic codebook, and they can up to 16 antenna ports. Okay, so that gives us more throughput. More throughput from here to there. Here also, if you see, we have 32 antenna ports and more bandwidth we have large antenna arrays like that. There are many features got added. Why we have added? Because we want to realize all these applications that we saw first. All these applications we want to realize. Okay, that is the aim of this particular talk. We will see what are the 5 features that they have added to enable this. I hope that gives us a good introduction. Now let's switch gears and go forward a bit faster. So we saw FR2 has this problem, 20 dB more path loss. And because of the extra path loss, how we can compensate is add more antennas. We can add more transmit power, that is one option, but that is not economical. Engineering wise, it's not economical. It is better to add more antennas. The dog is agreeing to that.
Oh, sir, 1 second.
No problem. Okay, so now we saw multi-path loss leads to more antennas. And now we can reduce the transmit power required on the UE. And now we can do 3D beamforming. We'll see what is 3D beamforming is. Okay, these are all things we can do. And now what else we can get advantage of line of sight channel compared to the non-line of sight channel in FR1. Okay, that means what I can do is I can direct my signal in one direction. Let's say I have this antennas and then I have a user here. I can focus my signal such that they add constructively here. And at the same time, I can focus to another user in a different direction. So I can give direction advantage in the line of sight path channel, which is available in the millimeter wave frequency, right? Anyway, so that is the, we'll see that part. Suresh sir, you can stop me whenever you want to give a break.
Sir, yes, sir.
Otherwise, I'll continue.
Yes, sir. So, shall we take 5 more minutes and then we'll break for some time, sir?
Yeah, I'll tell you some logical point here.
Okay, sir. Okay, sir. Right, sir.
Okay, so now let's see the same thing pictorially. Earlier, I had 120-degree sector in the sub 6 gigahertz case because I'm having enough gain for this antenna, number of antenna. Let's say I have 8 or 12, right? I have enough gain to give coverage of 10 kilometers. But now the cell has shrunk to 1 kilometer because of the path loss. In the FR2, to compensate that, I increase number of antennas. Since more antennas, I have now narrow beam instead of broad beam. More antennas means sharper beam. Okay, so that is good, right? We can get sharper beam means more signal out of it. But the problem is it become narrower in the angular domain. In the angular domain, it is more narrow. So now what I have to do, I have to sweep the antenna to cover entire 360 degrees. Or even within one sector, I need to sweep 4 or 5 beams to cover the same region, same angular area, right? Or same geographical area. Anyway, this eraser is not working very well. So how do we get it? Now that is what is obtained through what is called hybrid beamformer. We'll have more details later. And in this one, what we are doing is we have large number of antennas to cover the path loss, whatever extra path loss we got. But we cannot bring all those antennas to the processing. Let's say we have 64 antennas here. If we want to bring all the 64 to processing, that is not economical. Again, it is going to produce a lot of heat in the circuits. So we cannot do that. Even if I do that in the base station, mobile cannot afford more than 4 antennas or 8 antennas. It will be too bulky and not economical. So for that, what we do is we have more antennas here, but less RF chains here. And in between, we do some matrix multiplication to take this n RF chains to NT, number of transmit antennas. Some kind of conversion from one dimension to another dimension. You can assume it's a matrix multiplication. Same thing happens on the UE also. There are more antennas here, but less chains here. Okay, and this particular architecture is called hybrid beamformer because we have some analog beamforming and some digital beamforming. That is why it is called hybrid. Okay, and I have mentioned good tutorial papers. Whenever you get time, you can download and read them. I try to give as many references as possible. So in case someone is interested in getting more details, you can go to the references. So this is a logical point, sir. We can break now.
Yes, sir.
And how long going to be the break? And then are we starting MATLAB now or later?
Students, what do you need? Shall we do MATLAB exercise? Then we'll go for lecture, or we'll complete lecture, then we'll start MATLAB.
Sir, what I will do is I want to cover these at least two slides before we go to the MATLAB exercise.
Yes, sir. Yes.
Then they will appreciate that exercise.
Okay, okay, sir. Okay, sir.
So I will cover these two slides after the break.
Yes, sir.
5 minutes break or how long?
We'll take 10 minutes, sir.
Okay, so according to my watch, it is 3:20, 3:30.
Yes, sir. We'll start by 3:30.
Yeah.
Yes, sir. Yes, sir.
Okay.
Thank you, sir. Thank you, sir. Thank you, sir. Students, now you can break and you can join us after 10 minutes.
And you can post questions in chat box now. I will be checking chat box.
Yes, yes, yes. So far, no questions, only some answers. But students, you can also post questions in the chat box that sir is ready to answer them once.
Yeah.
Yes.
I'll be back in few minutes.
Yes, sir. Yes, sir. Akash Kannan. Akash Kannan. Akash Kannan.
Sir.
இல்லை ஏன்பா அமைதியா இருக்கீங்க ஏதோ கேளுங்க ஆகாஷ் ராஜ் ஆகாஷ் ராஜ் அரவிந்தன் அரவிந்தன் அரவிந்த் Aravind. They have gone for the break. Arun Pancharatnam, Panchacharam. Arun Panchacharam. It's okay. So we'll meet after the break.
Yeah, I'm back. In case you want to ask questions, feel free to.
Sir, student sir has come. If you want to discuss with sir regarding related to any questions or any questions.
Whatever doubts so far on whatever we have covered. Whatever doubt you have. One person's doubt will benefit multiple students because everybody might have same doubt and they are afraid to ask. So some bold person can come forward. And we are not going to put marks for this, so don't worry.
So some students have left. I think they may join within 2 minutes. I think.
Yeah, no problem.
Yes, sir. Yes, sir. Sir, there's a question, sir, in the chat box.
Okay.
It's a question from Jagata.
Yeah.
5G uses MIMO technology, which requires more antennas, which is not economical. How can we overcome this problem, sir?
Yeah. So the MIMO technology, it becomes not economical only when for every antenna you have a transmitter and receiver. If I have only antenna, that is very cheap. Now the challenge is shifted to the hybrid beamformer, what I mentioned. Let me go back to the slide.
Sir, kindly tell them about what is analog beamforming, what is digital beamforming, because they have not come across.
Yeah, we'll go through the details later. Yeah.
Yes, sir. Yes, sir.
Okay, so where we hybrid beamformer, right? So this is what I was mentioning here. You can have more antennas, no problem. Okay, sorry, I selected the wrong one. Let me stop sharing. Share. It's not allowing me to select one window alone. That's why I'm unable to solve it to one. So that's why we are having more antennas here because it's cheaper. You can have more antennas, but only this receiver electronics will be expensive. So that's why we have minimum or less number of receivers we have, and we need to somehow take the signal from to there and to there. That's where the hybrid beamformer advantage comes. Basically, there will be an analog beamformer which is done using cheap components. It has got a phase shifter and an attenuator, and it is directly works on RF signal. Here it works on sampled signal, ADC, DAC. So this does not need, this one does not need any ADC, DAC. 1 second. Hello?
Yes, sir.
1 second, Suresh. I'll be.
Yes, sir. Yes, sir.
Sorry about that. Let me go to the slide. So here it is built using cheaper components, analog beamformer, and that is how we are reducing the cost. Overall cost is reduced. Okay. And that's why it is called analog beamformer. The difference between this beamformer and this beamformer is that this has higher flexibility. More flexibility compared to this, less flexibility. So what does that mean is here yeah, so here I can steer the beam anywhere I want. I can steer any direction I want. Here I can only do limited. The beam width is broad and I can only do limited directions like that. Those restrictions come because of the cheaper electronics. However, it serves our purpose. Basically, we are able to reduce the cost, at the same time maintain the range. That is the advantage of going for hybrid beamformer, and that's how we solve the problem. So let me go back to the chat box. Okay, Jakata, does it answer your question? And if you have any follow-up question, related question, please come back. Yeah. Is all our back, sir? Can we start?
Sir. Yes, sir. We can start, sir.
Okay. So now let's look at how the physical layer of NR 5G is. I'll try to highlight the differences between the 4G and LTE and the 5G. Okay. In 4G or in LTE, we have only one subcarrier spacing. And as you know that we are using OFDM, orthogonal frequency division multiplexing physical layer technology, in both LTE as well as 5G. But there is a difference is in the orthogonal frequency multiplexing, you have these various subcarriers. This gap between the two subcarrier is 15 kilohertz in LTE. In 5G, this is supported. At the same time, we are also supporting another 3 or 4 subcarrier spacings. Okay. How does it gives us advantage is the question. So one thing is when you are going to go higher frequency or higher bandwidth, right? Let's say you have 120 megahertz here, and that from there we are going to, let's say, 200 megahertz, 10 times you increased. What does that mean? If I keep same 15 kilohertz subcarrier spacing, if I have, say, 100 OFDM bins here, that is going to increase to 1000 OFDM bins. That means that much size FFT, IFFT, all those things I need to implement. I'm assuming that students know OFDM. In case they are not, they will get familiar in the MATLAB exercise. Okay. So now by going to 15 kilohertz, what are we gaining? So basically the symbol, there is something called OFDM, symbol time. That means how long does it take to transmit one symbol, one OFDM symbol? That is equal to 1 by the subcarrier spacing plus some margin. Okay, this is going to be the time taken to transmit one OFDM symbol. Now, by going from 15 to 30, what we have done is by increasing subcarrier spacing, we made it half. Half of what used to take, or 1/4 of what used to take, or 1/8 of what used to take. Right? So we can use any of these features or subcarrier frequencies to increase number of OFDM symbols transmitted per unit time. That is a key improvement what they have provided. Okay. Why is that helpful? I have a low cost mobile which can support only 15 kilohertz. I can assign this mode. At the same time, I have an expensive mobile for which I use this to provide higher throughput. The best part is this, at the same time, I can transmit with two different subcarrier spacing. It is allowed by the standard. For example, if I draw time versus frequency as the 2D grid where the OFDM symbol is transmitted, so this will be one OFDM symbol. Okay. So this is 1, 2, 3, 4, and so on. Let's say this takes 20 megahertz bandwidth. I can define another band in parallel, same time, and I can use different subcarrier spacing here and different subcarrier spacing here, which is allowed because the base station can transmit up to 100 megahertz. Within 100 megahertz, it can split it into multiple sub-bands. For each band, I can allocate one subcarrier spacing. 1, 2, 3, and so on. So at the same time interval, if you look at it, I'm sending 3 different information in 3 different subbands to 3 different users. So that way I can have flexibility in choosing the right subcarrier spacing to increase throughput for higher demand. For example, eMBBB. One user may be a eMBBB user. This may be a YouTube guy downloading YouTube video in faster rate. He may be an IoT guy. He doesn't need more than, let's say, 10 kbps of data. I can use fewer resources and smaller subcarrier spacing because IoT devices are anyway cheaper. We want to keep it as cheap. So simultaneous transmission of different subcarrier spacing at the same time. And now remember, there is also one more diversity we have, is this antenna, which I have not brought in. So we have flexibility in different time, frequency, and antenna at the same time in subcarrier spacing as well. That's a key differentiation between 5G and 4G. Okay, how it is allocated in time. If you look at it in time, 0.5 millisecond, or you can say 1 millisecond as one of the another 0.5 is here, let's say, right? Not to scale. So within 0.5 millisecond, I can transmit 7 OFDM symbols here, 14 here, 28 here, and 56 here with the same 0.5 milliseconds. And now I have more resources, more time slots, I can accommodate more users. That is the advantage. So if you want to have massive machine type communication, or you want to allocate more resources for high throughput user, this can be dynamically changed every millisecond. So how I am going to allocate users here? Let's say I'm allocating this for user 1, as for user 2, say user 4, say user 6. I can choose the way I want according to the demand of the services that we are looking at. And that's how I am able to provide more throughput for the same bandwidth. And that is one. And second thing is, by increasing subcarrier spacing, I can also reduce the FFT size for the same bandwidth. Say if I have 20 megahertz bandwidth, I'm going to have, let's say, roughly around how many subcarriers? Let's take as 15 megahertz for just for convenience. So 15 into 10 power 6 divided by 15 into 10 power 3. So I'm going to get approximately 1000 FFT bins, right? Now, when I go to 120 kilohertz, so if I do 120 here, I'm going to reduce it by a factor of 8 directly. I'm going to do 128 point FFT. Okay, so that reduces hardware complexity. That is also another way it helps. So if you look at 5G, what is predominantly you will see is maximum flexibility in allocating resources dynamically to maximize the throughput of the network. That is the key point that you should understand. It was in LTE and others had a flavor of it, but 5G has taken this to the maximum level. Does anyone need help? Introduction on YFDM?
Students, do you need any introduction to OFDM? Do you need any introduction to OFDM by sir?
Yes, sir.
Sir, they say yes. Sir. I think you can.
Yeah, I mean,
Yes,
rather
sometimes,
than
yes, sir. Sometimes it's better.
rather than I explaining the whole thing, you can tell me what do you know in digital modulation. What do you know in digital modulation? Then from there I can I know what to give you after that. Do you know any digital modulation techniques? QAM, PAM, QPSK?
Students, kindly respond.
Someone please unmute and talk here. It will be easier, efficient.
Yes, sir. You know, sir.
Shyam, you wanted to ask, right? So let me know what you know in QAM or any digital modulation.
Sir, QAM is nothing but two amplitude into a single channel, sir.
Okay. Okay. So okay, let me take it from there. So in the case of QPSK, I'll take is here. I have I and Q coming from the QPSK modulation. So this I'm going to multiply by cos of the carrier and I'm going to multiply this by sign of the carrier, and I'm going to add them or subtract them, doesn't matter, and then amplify and transmit. This is what I do, right? Now, what you do is take this setup, cut and paste it multiple times. And what else you do is here you change this frequency as F1. Here when you multiply, see, these are all different symbols. I1, Q1, you have I2, Q2. And when you multiply here, you here also you change the frequency. This is cos F2, this is sin F2. And then add. Like that you have multiple copies. Then what you do is you again add all of them together before you transmit. So that's how OFDM is computed. This is one subcarrier spacing bin 1. This is bin 2. What does that mean is the difference between F1 and F2 is 15 kilohertz. In a loose sense, but anyway, I will not go into the exact details, but you get the idea. Basically, you in parallel, you transmit with the multiple subcarriers. Okay. And those get added together and amplified and transmitted. This is OFDM. Why OFDM? Because these frequencies are orthogonal to each other. F1, F2, F3 are orthogonal to each other. So that's why we have orthogonal frequency diffusion multiplexing. That's how the OFDM is modulated. In practice, what is done is this whole thing is implemented. This whole box is implemented using simple FFT. And that is what you are going to do in the MATLAB exercise today. Okay. If you have any doubt, ask now. Otherwise, you will be stuck in MATLAB step. Is that clear?
Yes.
Okay. Now I am going to ask you the question back to you. How will you use FFT? How will you use FFT for generating OFDM? Think about it, because it is, we are going to soon break for the lab. So I'm just elaborating on that previous point. Flexible subcarrier spacing or variable subcarrier spacing gives us different symbol time. Okay. So there is one more concept which I want to introduce in the OFDM. We have, let's say, for example, we'll take 128 point symbols or 128 parallel subcarriers, and then you are combining them with the FFT, and you are going to get 128 point output. Remember, this is IFFT, not FFT. That means this is treated as frequency domain, and this is treated as time domain. So once you have got the 128 point FFT, which is coming as a parallel array, you have to convert parallel to serial. I mean, sample by sample you transmit. Let's say first sample here, second sample here, third sample here, and so on. So you are going to have 128 samples, and that is going to take 128 times 1 by TS, which is a sampling time in the time domain. This much time it is going to take. And how do we fix the sampling time? Can I use 2 megahertz? Can I use 20 megahertz? Can I use 200 megahertz? What should I use as a sampling frequency or sampling time for the ADC? That is a question. So that again is answered by the OFDM subcarrier spacing only. We saw that we have multiple subcarrier spacing. Let's say 1 to n. So what is the bandwidth you are going to get? N times of subcarrier spacing, right? Let's take for example 100. So you are going to get 15 kilohertz into 100, which is going to be roughly around 1.5 megahertz. If my signal is occupying 1.5 megahertz, what should be my sampling frequency? Somebody answer that.
Students, please respond.
There is something called Nyquist theorem. You would have studied long ago, once upon a time, in the second semester or third semester. Anyone remembers Nyquist theorem? Sampling theorem? There are only two ways to understand this. Either you don't know, or you are testing whether I know it correctly.
Students, please respond.
So please respond. It's a fundamental question, right?
Yeah.
So for 1.5 megahertz, what is the Nyquist bandwidth required? Students, kindly respond. Oh, twice the frequency. Okay.
Okay, what is that number? Twice the frequency. 3
So
megahertz.
3 megahertz. 3 megahertz.
Ah, finally someone remembers it.
Yes, sir. Continuously many. Yes.
Okay, so I need to sample this as 3 megahertz. So 1 by 3 megahertz is roughly around 300 microseconds or 333 microseconds. Correct? Is it correct or wrong? Unit is wrong. Somebody correct it. 1 by 3 megahertz. Don't go for calculator. Think. How much is 1 by 3?
Microsecond.
0.333 microsecond. Okay. So now the total time taken by the symbol is 128 times 0.333 microsecond. So that will be the symbol time. Okay, sorry, not this one. Do it wrongly. Let me go back to the previous slide. So that will be the time taken by this OFDM symbol. Okay. And then there is something else sitting in between two symbols. If you notice, there is a grayed out. Between every OFDM symbol, there is something grayed out. This is called cyclic prefix, which is nothing but a copy of information. So let's say this is OFDM symbol. This is cyclic prefix. Let's say I take 1/4 of this symbol. I copy that here. Okay. Why do we do that? It's a reading assignment for you. Why we have to do this? When you are constructing OFDM, You have to read why you are doing cyclic prefix and what is the advantage, and you have to submit a report. Uh, um, Written report you can take maybe one week, or 1 week time should be enough, more than enough.
Yes, sir. Yes, sir.
So, and that will be considered for your marks, your report. Don't
Yes,
copy,
sir.
don't do mass copy. There is no use, because you're going to fail in the finals if you don't do mass copy. Okay, so this is fixed at typically, and we can have 1/4, 1/8, 1/16. Different portions of it can be copied, and you will understand why we have different cyclic prefix values. And one thing key is that only first symbol has different size cyclic prefix than rest of the symbols. All other 13 symbols will have same cyclic prefix except the first one, which is true in every subcarrier spacing. Why they have done it? They have done it such a way that the number of samples in the symbol is integer number. That means sampling rate times the OFDM symbol time, total time. They want this number to be integer. That's the reason they have done it. And now when you take all the 13 symbols with the TS plus cyclic prefix, it will not come close to 1 millisecond or 0.5 millisecond. It comes less than that. So the remaining thing they have put it as an extra cyclic prefix space. That is another thing you want to calculate and submit in the report. So you need to submit two things. One, OFDM, why cyclic prefix is required. Two, the size of cyclic prefix for, let's say, only 15 kilohertz of carrier spacing. And I want number of samples, not the time. I want number of samples. After fixing the sampling rate, I want number of samples. I want the samples in the cyclic prefix for the first symbol. I want samples in the symbol, then other OFDM cyclic prefixes. I want these three. So you need three: A, B, C. A is the cyclic prefix 1, B is the symbol time TP or TS, and C is the cyclic prefix 2 for other symbols. I want you to compute this and come back. In the that you have to submit in the written assignment. Okay, and it is very easy to use MATLAB for doing that. So that's it. Now let's go to the MATLAB assignment. How the MATLAB is available for everyone, sir? How is that?
Sir, everybody has got MATLAB, sir.
Okay, good.
So they have their our college license. They have.
Okay, good. They can do it now live.
Students, are you ready with the laptops? Hello. Kindly respond. Are you ready with MATLAB laptops and MATLAB? Yes, sir. Sir, they say yes, sir.
Okay, good. So let me explain the experiment. And you have roughly 1 hour to complete. Oh, actually, it's already 4 o'clock.
Yes, sir. Yes, sir.
Okay, let's give 30 minutes today.
Okay, sir.
Or we can even do it 15 minutes. Let them submit it later.
Yes.
That 15 minutes is only to ask doubts. If you have doubt how to code, you have to ask questions. The remaining 48 time, I will take the rest of the slides.
Yes, sir.
So it is given that you have 2048 point FFT you have to use, or IFFT you have to use to generate the OFDM symbol. Input symbols are all BPSK coded bits. When I have given the random bits, you need to convert bits to BPSK. If you have forgotten what is BPSK, go and read the textbook. Okay. Now, so what we have to do is basically you have 2048 FFT. The input to that all 2048 BPSK symbols. You are going to do IFFT for this. Then you are going to do parallel to serial conversion. And then what you are going to do is you are going to apply cyclic prefix to this. And to make it easier, I'll make it 12 symbols instead of in 1 millisecond, keep 12 symbols and all equal cyclic prefix just to make it easier for you. All 12 symbols have equal cyclic prefix. Instead of 14, I made it 12, so you get an even number. Okay, you will get equal cyclic prefix for all symbols. So you have to show me two things. One, what is a frequency domain spectrum? What is a frequency domain spectrum? And what is the time domain spectrum after taking IFFT and cyclic prefix? I want spectrum here and I want spectrum here. You can use p-Welch function for that. Read the help how to use it. There, the p-Welch you can specify the sampling frequency also. Specify the sampling frequency and decide how much cyclic prefix to compute, perform, and copy this portion here. And you have to submit the plots. Plot A, frequency domain spectrum. Plot B, time domain spectrum. Use p-Welch only for time domain. For frequency domain, you don't need anything. Because already in frequency domain, you need to only get this x-axis correct in this. And use log plot for the magnitude. Okay, basically you are use semi log y command to do this log plot. I want the frequency axis in hertz, the y-axis in dB, decibels, and I want what is the cyclic prefix size that you have chosen. These three information need to be submitted in the MATLAB code. As a form of MATLAB code, you know something called live editor in MATLAB, right? You have to submit as an MLX function, not .m function. Use something called live editor where you can intermix plot and code. You can step by step you can execute and it will keep plotting the whatever you are plotting. I want you to submit the MLX file. I don't want you to write any document. I don't want doc or any PDF files. I want only MATLAB code in live editor compatible format. And I will run each and every code and check. Okay. And if the two codes are copied, I can figure out immediately. If you want, you can make groups. It's okay to make 3-4 people as one group. Because we are going to have 4 or 5 assignments and I want you to rotate through different assignments and then submit the MATLAB code. Is the assignment clear? So you are going to use 2000 point IFFT. Remember, it is IFFT in MATLAB, not IFFT. You have to generate BPSK symbols from the bits. Okay. And then you have to do the spectrum computation for frequency domain, time domain. And you have to find how much cyclic prefix is required. This is the assignment. And you have another 10 minutes to ask doubts or write code. Actually, you can write code in 10 minutes and finish it. It is not that complex. And I have given all the function names, whatever is necessary.
Students, all of you, please start coding. Therefore, you will get, if any doubt, you can clarify them.
Yeah, while writing code, you will get doubt for sure. That's the reason we have given 15 minutes. If someone completes this assignment and you have extra time or weekend you want to spend, I have one more assignment after that. I'm just flashing it. You can always get it through the recording in case you have doubt. And whoever submits this assignment successfully will get an interview call from me to join my company. Basically, if you want to work in 5G or wireless communication or signal processing related work, your senior Deepan has joined us. You can check with him for any input. Deepan Vetrivel, 2 years senior to you. You can ask about the work nature, and we are in Bangalore. If you want to join a core signal processing job, we have 2 openings. It's up to you to grab the availability.
Students, kindly make use of this opportunity. Those who have placed and other software companies, now you can look for core company placement. SAR is ready to offer you. You need to code only. You need not do anything. We may have an interview, but the first thing is you need some simple MATLAB code. Please make use of this opportunity.
You can use Google, whatever you want. You can search in the net, whatever you want. But don't copy from others. Because in the interview, I'm going to keep the code and ask you questions. So I'll figure out whether you copied or not. There is another way to get job interview. I'll give you that option also in case someone doesn't know MATLAB. I don't want to penalize them. You can write a written test, which will be much harder. I'll tell you that. You can take a written test in TCE. Tell me when you are ready. I'll send it to the placement officer. But I would suggest this is an easier path. Writing MATLAB code is an easier path.
Sir, Ganesh sir.
Yes, sir. I'm here.
Sir, I have a doubt.
Yeah.
In the multiple numerology, due to switching, will it not create any problem in the hardware?
Good question.
Because when switched from one subcarrier to another subcarrier, the timing and all, will it not create any problem, or whether those problems are solved, sir?
Actually, you have already solved the question yourself. So think about what will be the OFDM symbol time for different subcarrier spacing. The answer lies there. Otherwise, I'll take it offline with you. Yeah.
Okay, sir. Okay, sir. Okay, sir.
Yeah, it is just question of aligning these time domain in time domain.
Yes, sir. Yes, sir.
And one more thing, what they will do is they leave a guard band between two different subcarrier space windows. They give a guard band.
Sir, then how then receiver will identify which is coming and which subcarrier it is coming, and based on that it has to take its particular
Yeah,
length, no, sir,
so
for
basically
demodulate.
the receiver will be told which waveform, which frequency bin, which time slot. They'll
Oh,
give.
that information they transmit.
Yeah, they transmit a prior. Yeah.
Oh, yes, sir. Yes, sir.
They default they start with 15 kilohertz.
Oh, sir, yes, sir.
Then later they can switch to whatever they want.
Oh, right.
Yeah, a lot of interesting problems are there in this.
Oh, yes, sir. Yes, sir.
So that's where signal processing engineers have work, right?
Yes, sir. Yes.
Okay. Any doubt? We have another 5 minutes left. Actually, almost time. I'll give you another 5 minutes to ask questions. I'm only asking you to submit exercise 1. I'll repeat that I want a frequency domain spectrum as a log versus frequency or dB versus frequency plot. Frequency in hertz. B, I want you to take the IFFT, add cyclic prefix, and then do a time domain spectrum. Again, same dB versus frequency hertz. Here you have to use the sampling frequency of 30.72 megahertz. And C, I want you to tell me reason for cyclic prefix size. I want number of samples, not time. And I already given a clarity that you are going to generate 12 OIFDM symbols, which is equivalent to 1 millisecond worth of time. After adding cyclic prefix. These are the 3 things I am looking for. And I want it in a MATLAB live editor format so that I can execute it easily here. Okay. I'll give you 5 minutes more, and then after that we get started. A lot more slides to cover. When you are taking a plot, spectrum plot, do it for together all the 12 symbols in the time domain. In the frequency domain, you can have just 1 or 2, or 1 is enough. 1 symbol OFDM is enough. Or if you can average it, it's also fine. You can average over all 12 symbols, it's fine. Plus one more written assignment we talked about is OFDM generation using FFT, how it is done, and why cyclic prefix is added. So this is a written assignment. You can use handwritten or typed, whatever you want, whatever you like. Word document or LaTeX document, anything PDF is acceptable. Handwritten and scanned using Microsoft Lens for PDF is acceptable. And send them to Rajeshwari madam.
Okay, sir.
Okay, sir.
I'll take it from you, ma'am.
Yes, sir. Yes, sir. Sure, sir.
No, I don't know whoever is representing this course. I don't know whether you or Suresh, sir.
Sir, both, sir.
Both are representing.
Okay. Yeah.
Both are
Then
representing.
we'll ping pong between you for a different assignment.
Yes, sir. Yes, sir.
You can also post questions in the chat box. I'll monitor them now. Sir, I'll be back in 2 minutes.
Yes, sir. Yes.
Okay, I'm back.
நீங்க வந்துட்டீங்கன்னா இல்லையா எனக்கு உங்களோட
Shall we get started, sir?
Yes, sir.
Okay, so I want your attention back on the slides. There is more stuff, interesting stuff is there, and I want to cover a lot of ground. So we saw that the 5G system must have multiple beams to cover cell radius for two reasons. One, that path loss is higher in the millimeter wave frequencies, and two, we need to we cannot transmit a higher transmit power, so you increase number of antennas. Once increase number of antennas, the beam becomes automatically narrower. That means, given a sector, 120-degree sector, I'm going to end up having multiple beams and I have to sweep it through so that the area is covered, right? You can choose how many number of beams you want to choose. The standard doesn't specify that. However, you need to scan it often, and when you're scanning, you should also remember if user 1 is found here, you should remember that, okay, for user 1, beam 2 is the correct index. For user 2, say 10 is the correct index. Like that, you should remember that also. And this beam management itself is a big interesting theory, and practical aspects are there. There are 3 phases of beam management. One, initial acquisition, where the base station and UE are not connected. You just starting, you just turned on the mobile phone, right? During that time, they have no idea when there is a beam and where there is a beam. How do I get it? Cut the correct beam. So this guy has multiple beams. This guy has multiple beams. There is only one unique combination which is correct for both of them. So the base station has to select one beam. This guy mobile has to select another beam, such that you get a good SNR. That is a whole idea. We'll go to the details next. Then first you start with a broad beam, okay? So that you can do less number of scanning. Initially, you don't know where the user is. So let's start with 2 beams. Then later narrow down to finer beams. So that's what you do. Then what you do? You keep tracking the beam. As the user moves, you should keep tracking the beam. And this is narrow. Broad to narrow. Initially you start with broad, then go to narrow, then from narrow you do the tracking. So these are 3 phases in which the beam has to be maintained to make sure that the user and the mobile and the base station are connected all the time with a good SNR. So that becomes even more challenging in FR2, because we saw there more number of antennas are used to compensate for less transmit power. So more beams, more antennas means even narrow beams. You cannot get a wide beam like this. Okay. So those are the challenges. Let's see how we can get it. Initial access. Initial access is when the mobile is trying to listen to the base station. Okay. What base station does is it transmits periodic broadcast channel. Physical broadcast channel is BCH. It transmits periodically. Not only that, it also transmits periodically with different weights. It is same information transmitted multiple times with different weights. So let's say this is weight 3, the same weight is used again, same weight is used again, and then you have weight 1, weight 1, weight 1, then you have weight 2, weight 2, weight 2. So when the mobile is there, it is also changing its different beams. It's looking at different beams. And then as it listens to this entire PBCH transmission, it will keep trying to listen to the correct, it will try to listen to the PBCH decoding. When it is able to decode PBCH correctly, it will assume that's a good combination of beams, both the receiver and transmitter. And that they call it as SS block. SS stands for synchronization. That is transmitted multiple times in different blocks in different weights. So this is weight 1, weight 2, weight 3, weight 4, weight 5. You can switch the weights immediately, or you can even have a block of symbols with the same weight and then switch the weights. So you have to sweep it such a way that you are able to cover all the beams in the sector within a prescribed time. What is that prescribed time?
Ganesan sir?
Yeah.
Sir, you mean the weights are beamforming weights?
Yes.
Okay, sir. Thank you, sir.
And what you have to do is 20 millisecond is the time with which the PBCH is repeated. This is the PBCH repetition interval. Within 20 milliseconds, you can have multiple PBCH also. That is also allowed. Okay, they allow 4, 8, 16. In fact, we go to FR2 up to 64 is allowed repetitions. I'm ignoring those details, but idea is that you keep sweeping the beam and let the mobile choose the right beam for him, because he's the guy listening to it. He knows what SNR is seeing, right? So after listening to the, after selecting the right beam, remember these beams are broad beams, okay? Even though it's drawn like this, but there are broad beams. There will be overlapping broad beams. Let's say this guy is selected, okay, this is my best beam. How does it convey to the base station? It has no notion, it has no connection of resources, time domain and frequency domain resources. It doesn't know where it can transmit. Okay. So that information is conveyed to the base station in an indirect way. So initially, the both of them sweep the beam and select the right beam. Okay, and it is confirmed through this mechanism. It's called RACH, is uplink random access channel. So what he does is, the mobile, as soon as it has selected the beam, it knows that after 20 milliseconds, again same beam will come. So it waits for 20 milliseconds, and then there is an offset location from that PBCH to PRACH window. It's a fixed window. That information is sent in the PBCH actually. Once you know PBCH decoding, you know where to look for PRACH. So you send a request for connecting to the network. So he sends the transmission in that window where the base station also expected to keep the same weights here. It will keep the same weights here and there. So W1, W1, W1. So the base station, if the base station can decode PRACH correctly, then the base station knows what is the right beam for the given user. That means for every mobile user, the base station must know and track the correct beam ID. Okay, so the beam ID is tracked by base station, not the mobile. Mobile blindly decodes a signal and sends the PRACH and sends a SNR report. That's all it does. After selecting the broad beam, the narrow beam is selected through something called Channel State Information Reference Signal, CSIRS. This is a special training sequence which is has a special weights designed for a given UE. For every user, The CSI RS is transmitted in different time slots, depending on the signal strength, attenuation, fading, all those things are taken into account. So this is a training sequence. Channel state indication reference signal. RS stands for reference signal. Transmitted by G node B or base station to the UE or the user. For each user, a separate CSI RS. And what he will do, he will also code it in such a way that he is transmitting narrow beam. And what code is used is already communicated to the UE before he sends the coded beam. And what the mobile will do is mobile will measure the channel information, the channel quality indicator, channel rank, everything it will measure, send it to the base station. Then the base station decides what is the best beam to select. That's how the fine beam is selected. See, remember, it is only pictorially I'm explaining. In reality, there's tons of signal processing goes underneath. You should know how to estimate channel. You should know how to estimate the time delay between the mobile and the base station. You should know how to send this channel quality indication, how to quantize the information, the SNR, and how to estimate the channel rank. Everything has to be known by the mobile so that the base station can select the best beam. Okay, that's how that is done. And in the uplink, there is also, okay, so let me explain this, then come back to the uplink. So what we are going to do is the SS burst, where the broadcast channel is repeated multiple times with the different weights, that we call it beam sweep and measurement. So you should decode, condition is decode PBCH without CRC error. And if you have multiple beams where you can decode correctly, select best SNR. If multiple beams are good, select the best SNR beam. Okay. And then you send the, yes, you select the best beam. And then you send the ratch in this. This is a ratch. And if the base station receives it correctly, it sends an acknowledgement, ratch acknowledgement report. In the ratch acknowledgement report, it tells you which frequency bin, which time slot is allocated to you. It is finally in the RAR where you get the information about this. Okay, then further handshake goes on. Initial synchronization is this much, it is done. Any questions so far? Remember, this is happening for every single user. Every 20 milliseconds, it's repeated again and again and again. Imagine the complexity of the base station. Okay. So that's what we saw initially. The same thing verbally I have explained here. Downlink PPC transmission from the base station. Okay. Then for each repetition, different beam weights are used. For each beam index, different training sequences are transmitted. For each beam position, RACH window is scheduled, and mobile sends a RACH request in the correct beam number in the RACH window. This is the overall flow. Same thing, I'll show you one more picture. See this? These are all different repetitions of PBCH or SS burst. SS stands for synchronization signal. And then for each corresponding location, there is a CSIRS sent. So you can estimate your channel for that particular beam. Okay. And this all information is sent to the base station so that base station can take a decision. Same thing pictorially mentioned here. You can select multiple beams where you are able to decode correctly. Later, when you are doing fine beam selection, the base station will do weighted sum of these beams to create this beam, which is good for you. Okay, these are all algorithm used by the base station. You don't have to worry about it, but this is how the beam selection happens. And this beam selection is continuously modified. When the UE keeps sending SNR report or CSI RS report, it keeps sending it periodically, and then base station keeps adjusting the beam weights. That's how the link is maintained. Suppose, let's say suddenly the mobile is blocked by a bus, right? Between the base station and the mobile, the bus came. So what happens? You lose this signal. So your SNR will be poor. You will report a poor SNR. Okay. And once the SNR report is received or not received, the base station knows that you have a poor signal. You have a poor link. It will go back to the beam scanning again to select the best beam. Again, it's quite involved. I'm not going through the full details. The standard is very, very, very complex. But if you understand the mechanism, you can read it and then understand the fine details later. And there is coding for each frequency band separately. I'm not going through that. Basically, you can have a wideband code or you can do subband code. You can right now skip it for now. Okay, so that's how this whole data transmission is initiated, or the synchronization is done. Initial access is obtained, even though the base station and the mobile are blind initially. They don't know what is the right weights to start with. Once they have weights, then they can communicate the data channel through which they can mention what is the best beam, and all those things can be communicated. Now, whatever we saw is the downlink beam selection. On the uplink beam selection, it has to be done by the mobile, right? So that is done through something called sounding reference signal, which is another training sequence transmitted by mobile and the base station checks what is the best beam. Again, this guy will switch the beam here, his beam. Base station selects the right beam and then it gives feedback. It uses the beam the best beam suggested by the selection part, and that is used to transmit the RACH preamble, next RACH preamble. So the mobile sends the SRS, The base station selects the best beam and it sends a SNR report. Okay. Oh, sorry. Let me correct it. So the best beam selection is done by the base station, by the mobile, based on the CSA RS, and then he also gives that information to the base station. Then base station uses that to schedule the RATs. That's how it is done. And the base station also monitors the SRS in continuously to check whether the mobile is within the reach or not. And base station also estimates the channel in this direction, uplink direction, because the downlink channel and uplink channel can be different if it is a frequency domain duplexing signal. Okay, that's how the uplink beam selection is done. So that covers today's portion. I will give some aspect of the higher layers or the hybrid beamforming part. Let's see how much we can do today. So this is how the hybrid beamforming is done. What do? You create these OFDM symbols for each antenna. Okay. This is not the physical antenna, but logical antenna. This is the physical antenna. What is the difference between physical antenna and logical antenna? One logical antenna gets connected to multiple physical antenna through phase shifters. That means if I am transmitting a signal, I can create an analog beam which is broad and send this signal. Okay. And I can, if I have multiple antenna array, I can create multiple broad beams and transmit same information or a different information. Okay, that is also done by this multiplexing part here. So now this various logical antennas, 1, 2, 3, decides how many spatial layers or how many channel can be multiplexed together. That means same frequency domain resource, same time domain resource, but different spatial code. So that means simultaneously within this broad beam, I'll have multiple narrow beams and I can use it the way I want. Why narrow beams? These are all assigned to different users, UE1, UE2, UE3, UE4, and so on. So we are able to have a broad beam in the analog beamformer, and the fine beam is done by the digital beamformer. This has a very good accuracy. If this is 6 bits, this will be 16 bits or even 20 bits, because this is completely digital. The weights are digital here. Here the weights are analog. That is how we are able to generate multiple beams simultaneously using the hybrid beamformer architecture. I hope this answers the question someone raised. Someone asked how we are able to do the hybrid beamforming and in a cost-effective manner. This is how it is done. Why it is cost-effective? Because this is the ADC, DAC, mixers, receiver. This is only a smaller number compared to larger number of antennas. Antennas are cheap. Receivers are not cheap. That's how we are reducing the complexity. And how now if you zoom into one of these, this is how it is done. So basically we'll have the common data coming, and which is ADC, DAC and everything. and so here is the analog beamforms are here, and you control what data goes to which antenna, which physical antenna. Okay, that's how it is done. So yeah, just an example is we can have 64 antennas here, and we have only 4 antennas going to the base station hardware. This whole thing is called radio unit, or RU. Or RU, or there's another name is RRH, remote radio head, different names depending on the capability of that. Okay, so now this is what, only this part is mounted on the tower. This part is the base station part, or the baseband unit part is one common for multiple RUs. There can be multiple RUs. They are all connected to this via fiber optics, high-speed link, and then one base station controls multiple towers, multiple sectors, like that. So using that mechanism, you can reduce the complexity. You don't have to have air conditions, multiple air conditions for the base station units. If there is a dense area, like I said, town hall road, you can put multiple of these guys. You can put multiple of these RUs across town hall road and have one common baseband unit, maybe say sitting in Meenakshi temple. Right? So around Meenakshi temple, you can have multiple RUs controlled by one base station. Anyway, Meenakshi controls everything in Madurai. So yeah, that I think I'll skip these slides. These are all a bit involved. We did not cover that part today. And this is the core network. What is core network? This is the backend part which we did not talk today. You have the UE talking to the G node B, which is a base station. One or many. Okay, you can have multiple base stations. Again, one or many. This particular link is called Radio Access Network, or RAN. Today we saw a small portion of that RAN. Only this much related to beamforming we saw, but there's a whole lot of stuff which is there in the G node B, which we did not look at it today. Basically, all the MAC protocol, RRC, RLC, PDAP, there are so many layers, right? RLC. So this is layer 2, up to this is layer 2, then layer 3, layer 4, and so on, right? So this is the OSI layer, what I'm talking about. Now, these GNBs are all connected to what is called core network, which is the actual intelligence. This will be one with Airtel, one with Reliance, different one with Reliance, and so on. One with Vodafone, and so on. So this core network is the one which actually defines a telecom operator. Today, if you look at 4G, the telecom operator takes everything up to this and then controls. Every base station, antenna, everything he controls. But what is going to be done in 5G is this: the telecom operator need not own these base stations. They need not own these base stations. This can be owned by some third party who rents this base station to to these companies basically. Same base station will be connected to this. Sorry, not this. This multiple core network. That means they will be time division multiplex or frequency division multiplex, and they will be reused according to the load. Okay, suppose in the night there is no load, they can shut down one entire base station, and all of them will use one single G node B. That way, the operation efficiency improves, their cost comes down. Now, this core network is a beast, which has all the intelligence of the telecom operator. What are the things it has to do as a telecom operator? First thing it should do is that it should register you in the network. You should recognize you are a valid SIM. Recognize valid SIM for Airtel or any other operator, right? Then convey the network parameters. Manage mobility. Manage billing. How much time you spent and browsed and so on. Then manage load across base station. Manage load in the network. Like that, there are a zillion functionalities it has got. And that's all addressed by these various boxes in the G node B. Why they have done like this is, again, they made it simpler, modular. For example, you can buy this box from Ericsson or Nokia or anyone else. This you can buy from somebody else. This you can buy from somebody else. And you just connect all of them together, it will work as your network. That's how they have disaggregated the hardware and software. And 99% of this software runs on a cloud. This is another key development. Now it is cloud RAN. It runs on the cloud. So that is the, again, major change. And I highlight few functions. You cannot go through each and everything. AMF is access and mobility management. This is the first guy who will register you. Then session management will give you call resources, IP address, internet connection, all those things. Okay. Then the UPF gives the gateway switches. This is the one which takes you to the internet through the DN, data network. Okay. And what we saw today is only this particular interface. That's where the physical layer is. So we are like maybe like Avayar சொன்ன மாதிரி கட்டுறது கைமண் அளவு தான் இருக்கு, அல்லாத உலக அளவுன்னு நிறைய இருக்கு. So it's lot of information is there, and I think if you understand the 5 level today, I think it's good enough. I'm just only giving you the whole picture so that you understand how much complexity is there in the system. Yeah, with that I conclude. It's already 5 o'clock. Any questions, comments, doubts, let me know. Another 10 minutes, I'll wait.
Students, please get to come. Sir, there's a question in the chat box, sir.
Yeah, I see that. Radhakrishnan, even though 5G electromagnetic radiation are non-ionizing, by using 5G techniques, we are able to scale up connection density to 1 million devices over 1.5 years, increasing the programming. This is safety. Well, it is not a major issue, but it's a long answer. I'll make it short. For every frequency that is used for transmission, government sets up what is the maximum power you can transmit, including the beam, even including the beam weight. They'll tell you what is the maximum transmit power that is allowed, and that is computed based on whatever is the safety limits for human body. It is not that you are going to sit next to the base station. The base station may be sending 200 watts power or 100 watts power, whatever may be the number. But you are going to be at least a kilometer or 2 kilometers away from it. By the time the signal gets attenuated very fast, remember it is millimeter wave frequency or even the radio frequency. It is microwave frequency where it is attenuates very fast. So it is within the safe limits, but I don't want you to climb the cell phone tower and say that I am radiated. That you are not expected to see. If you go stand next to the antenna, yes, you will get fried, but you are not supposed to do that. Pon Radhakrishnan, you can read about something called SAR, surface absorption ratio. You can look at in Google, and that'll give you more details on how the absorption of electromagnetic energy into the human tissue is measured and how the safety limits are mentioned.
Okay, sir.
Students, if you have any queries, please clarify from this sir.
Sir, I have one question, sir.
Ganesh sir?
Sir?
Sir.
Sir, madam has got a question.
Sir,
Yes, ma'am. Yeah.
Sir, so in your slide, under the heading combining analog and digital beamforming, sir. So actually, each user is allocated with a one YFDM symbol, sir. Is that the meaning of that slide?
Okay. Let me go to the slides.
Combining analog and digital beamforming, sir.
Yeah. So basically, how it is done is, in a crude way, you can easy to understand is the time and the analog beamforming is done in time domain.
Okay, sir.
And the fine beam is done in frequency domain.
Okay.
Okay, so why it is I'm saying that is that
Yes,
so you have, let's say, one signal,
okay, sir.
right?
Yes.
This I'm going to send it to multiple antennas after bringing a phase shifting. This is like your regular uniform linear array.
Okay, sir.
By selecting the phase shift, I can create a beam.
Yes, yes.
But this, if you look at one segment,
Yes, sir.
if you have, let's say, 4 antennas or 8 antennas, let us say, 4 or 8 antennas, or even 16 for that matter.
Mm.
Depending on the number of antennas, even though there are so many antennas,
Mm.
you don't excite all of them. You can only select a subset.
Okay, sir.
And then so that you can make this beam broader.
Okay, okay, sir. Okay, sir.
Now, what happens is this signal
Mm.
comes from after the spatial multiplexing. There are multiple users coming here,
Okay, sir.
and they are given different frequency resources. F1,
Yes, sir.
F2, and then waveform signal combines all of them.
Okay.
This is waveform symbol. It combines different frequency resources. Now, how do they retrieve it? Before combining, they put different weights for each one of them. W1, W2, W3. So what you are going to get is
Yes, yes.
WIXI, which is then this whole thing added with
Okay.
UIYI. These were different users.
Okay, sir.
Then VI, ZI, like this, they are added
Okay, sir.
and then transmitted. So now this weights will give you the fine beam, which is digital beam.
Okay, sir.
That's how it is done.
Okay, sir. Thank you, sir.
Okay, any doubt on assignment?
Sir, can you share that 5G test code development, the big project from the TRI?
What is it? 5G?
5G test bed development. All you have
Okay.
joined along with all IITs, no, sir, to develop a test bed.
Yeah.
Can you share what is the current status or how far the India now progressing towards that?
Yeah, they're testing it. It's working now. Basically, the hardware software integration is done.
Yes, sir. Yes, sir.
And now, in fact, IIT Madras is going to go for a field trial within the campus.
Oh, right, sir. Right, sir.
Yeah, I think the project will come to an end this year.
Oh, yes, sir. Yes, sir. Yes,
Yeah.
sir.
It's all working fine. Yeah. Now, of course, they have done a small portion of it, not the entire thing.
Oh, sorry, sir.
But it is good enough to have a call.
Sure.
They can demonstrate a call or send a video.
Oh, sir.
Yeah, the entire base station they have implemented.
Yes, sir. Yes, sir.
And the core network is implemented by IIT Bombay.
Oh, yes, sir.
Yeah. So they have complete end-to-end system they have.
Oh, yes, sir. Yes, sir. Students, kindly complete the assignment and then send us so that we can send the codes to sir, and sir will look into the code and call you for interview. Maybe a week. Maybe
Yeah,
a week.
1 week should be good enough. Yeah.
1 week. Okay. 13th. Okay. So 13th of so the deadline is 13th. Kindly complete the code and then assignments. Send us. We will send to the sir so that sir will
சார் இது நவராத்திரிக்கு எதுவும் லீவ் இருக்கா, பிரேக் இருக்கா?
ஆமாங்க சார், நமக்கு we are ஆமா சார்,
14 onwards we have leaves, sir. I think
14th ல இருந்து 18th 19th வரைக்கும் லீவ் சார்.
ஓகே ஓகே ஓகே.
And from 20th they have tests, their CAT 3
ஓகே ஓகே ஓகே.
continuous assessment test.
Okay, okay, okay.
So students, similarly we have one more lecture on coming Saturday and Tuesday.
yes, yes,
Tuesday.
9th and 12th.
9th and 12th. Yes, sir. On 9th it is for the 5GNR students, and for 12th it is wireless students. So we'll send you the schedule. You join us on Saturday. That will have a little bit additional stuff related to 5GNR. So hopefully you will get more insight into the multiple antennas technologies in 5GNR. So shall we complete, sir?
Yeah, I think you can stop the recording.
Yes, yes, sir, yes, sir. So okay.
Yeah, I'm done. So I
Yes,
think
sir, yes, sir.
looks like students understood everything, so it's fine.
Yes, sir, yes, sir. So on behalf of our department and our institution, we thank Dr. Ganeshan sir for spending the entire afternoon with our students and taken the toughest job as a very, very light, and then so that students can easily understand the topics. Definitely it takes even a month time to read this material, I think, sir. You have compressed all those materials and then given as a gist or given as a very good understanding material to our students, sir. So that was a very nice explanation, or the explanations are easy to understand by our easily understandable by our students.